Conditions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
How's everyone doing today? We got Shiv here, we got Anjali here, we got Max here, Matthew, Megan, good to see you here, Bon, good to see you here. Who else we got in the chat? Say hey if you're in the chat. Make sure Mubot sees you. He's always here watching in the background, giving those points. Anna, Lucas, Nathan, Megan, Kevin, Turner, Wilton, good to see you here. How's everybody's day going? Lindsay, hey Brian, good to see you here, Kevin. Good to see everybody here. We're going to start up here in a second. What were we talking about last class? Oh, no, we got some injured football players. Not good right there. What were we talking about? I'm not asking myself. I'm asking you to see if you remember what we were talking about last class has something to do with this right here. How many hours does it take for one bonus point? A lot. Well, not the hours. The hours doesn't count. It's the points. Getting close right there. I think it's 20,000. Getting close. And then it's 50,000 to the max. So keep going right there. Keep showing up. Hashtag show up to get those points. We'll throw out 50 more points right here. What was the topic from the last class? And so I do want to mention one thing to start, though. And so if I emailed you, don't worry. Like some people just miss the assignment. That's okay if you have drops. But what you don't want is you don't want to miss multiple assignments. Missing one assignment, no big deal. Missing two assignments, still you get the drops. Missing three is where the problems come into play. So I do think it's 100% fine. And thank you everyone who reached back out. Matthew, good to see you here. But if you're stuck on anything, I don't think we have 13 jokes yet. We'll get there someday. If you're stuck on anything, please let us know. And I want to point this out. What's better than making a 0 on the assignments? What is better than making a 0 on the assignments? Even if you feel ashamed that you would get this grade, what's better than making a 0? If I were to walk up to you right now and if I were to hand you $25 right there, Max, would you turn that down or you say, nah, I prefer 0? Megan, if I said, here's $50, you'd say, nah, it's 100 or nothing for me. I'd prefer $100 over $50. I would. That's a true statement right there. You want to offer me $100 to $50, I'll take it. But even if you start the assignment, even if you have something, turning it in is going to get you a lot more credit and be much better than getting a 0. Good to see you here, Alyssa. Let's run another 50 points, everyone here. So I do want to remind you of this. Please start after forgetting to submit a fully completed one. I'll definitely take a 25 over nothing. Exactly. So don't worry if you submit something and it's not 100%. That's all right. The assignments are a little bit long. They're a little bit difficult. And here's the thing too, swing by office hours and ask questions during office hours. I'm so worried. I don't have a bunch of 320s coming by and saying, hey, Brian, how do you do this problem? But swing by office hours, say, hey, Brian, how do you do this? I think I saw some people using the 320 TA hours, which are excellent. But swing by, say, hey, Brian, can you work this problem? I know they're mainly due on the weekend. So maybe people are waiting till the weekend and then they're stuck on the weekend. But just take a look early and be like, hey, Brian, I don't know how to do this one. Also, I do want to say this. I'm throwing another 50 points. Thank you for everyone using the Discord. Has the Discord helped you, yes or no? Feel free to put no in the chat. Who here has gotten help on the Discord where you were stuck on something wasn't loading, maybe you forgot to load reg class, you didn't load the data, you just forgot a comma or something, but you put something in the Discord chat and you said, hey, this isn't doing this, and someone's like, hey, do this. I'll tell you this much. Some people are quicker than me on the Discord, and I feel bad because they're replying. I'm like, they already answered that. I shouldn't be replying. Megan says yes. I'm seeing it this semester. I'm really seeing it. So if you're not on the Discord or if you're stuck on something, putting it out there in the general chat, jumping into office hours, messaging me, absolutely, Matthew says right there. And maybe that's the thing. Maybe there's a lot more Discord utilization with our class. I just want to make sure everyone's getting the help they need because this class is like a train. And if you just let the train keep going, it's going to get further away from you. But don't be freaked out. I want you to just take a moment. If I have a question, someone has already asked, it's on Discord. Angeli right there. I'm so glad to hear that because you can look through what people are asking. We don't use the chatbot, look at what other people are asking. If you have a question, someone else might have already had it too. Exactly. And I think that's what's so great is on the Discord, sometimes you don't even have to message me. No, do message me though. But if you put it out there in the general chat and then someone's like, hey, this isn't working, you can look at the general chat and a lot of great things have been answered. And is Parker in chat today? Parker's our class, right? Because, man, Parker's just, he's an all-star. 100 points out there for Parker. We're just going crazy on those points. Remember, hashtag show up, get those points. Parker right there. I want to give a special thank you to Parker. One night I was answered emails for like 2 or 3 hours, and then I looked and Parker had answered every question. I was like, well, Parker just Parker just went through question by question, answered them all. And how many points can you get on your grade by interacting on Discord? Now, Parker might be there. How many points can you get on your grade by interacting on Discord? What is the max bonus that can be obtained by being part of Discord, interacting? So it's an important thing to know right here to get extra points. How much can you get on your grade by just being on Discord, talking and interacting? And Parker, are you there yet? Have you gotten it? Parker might be there. I should look at the ranks. Was there on the first week. So in other words, you can get there. I think Parker, yeah, we've got the gaming channel, so you can talk on the gaming channel, the sports channel. We could make other channels if people are like, hey, I really want to talk about Bachelor. Don't tell me what happened this week. Don't you tell me what happened this week. But you can get up to how many points on your grade? Could you explain the max bonus? So you can get 1.2 from Mubot. So Mubot gives you max 1.2 and 1.5 Discord bonus. Parker's just one of us, or one of you. And so Parker's just rocking out right there. Parker, some extra points right there for making people think you're a TA, which is awesome. Well, we could do that. I'll avoid that because I don't watch it soon enough. Should we put that channel? Should I go make that channel right now? Let's see right here. Watch this. Social. So let's go here. New channel name. Bachelor discussion. Okay. I might regret this. I am avoiding this channel in case of spoilers. Okay. Okay. There's a new Bachelor Discord discussion right there. Don't. I'm not talking about this week. No one tell me about this week. I didn't see. I think it's last night, right? Didn't see it yet. I have to wait for it to go up on Hulu. So there we go right there. There are the points. So any last questions right now before we get started back on today's topic? Any last questions? We're going to jump back into correlation right here, but make sure to understand that you can get tons of points by interacting. That's one of the key things right here is you can get tons of points by interacting and being part of Discord, being part of this chat right here. The more you interact, the better. That's what we want. That's how to be successful right here. Swing by Office Hours. Have any questions? I think you can do rank. There's a rank check channel. So go to where it says rank check and just do !rank. If you have any issues, let me know. And I'm going to go to the rank check channel. There's a rank check channel so that way we don't clutter up other channels. So you go to rank check and then you go !rank. I think someone just did. Oh, everyone's there right now. My number one. I am number one. So you need to get to level 5 to get the points. And maybe I'll make it higher. So everyone's checking their rank right now on the rank check channel. I think it goes away after a while on the rank check channel. So yep, people found it. There you go. That's so we don't just clutter up other channels with checking ranks because you can do it anywhere, but you know, we keep the discussions to what channels they're in. Awesome stuff. Let's hop back here to start talking about some simple linear regressions. Kevin, thank you so much. And 50 points, Kevin. Great question. People started doing that immediately after you asked. You said, how do I do that? And I said, there's a rank check channel. Do we get points for interacting in the Bachelor discussion? You actually do, Megan. You actually do. So I like it because it's a little bit of community building. So Megan, you get points for going on there and talking about your thoughts on Bachelor. That's the way we roll. Let's hop over here to the notes and start up some learning on some simple linear regression. So when we're doing simple linear regression, so see, I was in a class where I got points for doing it. So we only get 1.7 points, correct, only up to 1.7. I should have maybe put on some extras, but it's what we agreed on as instructors. So, and actually one of them just emailed me and said, hey, Brian, what's the system we agreed upon? I mentioned it. I always adjust what I'm doing. So it is up to 1.7, not a total of 2. Good questions right there, Lindsay. And Mubot will tell you, for those who haven't seen, if you do your ! points, now I'm at the maximum points. I got all my points. It is harder to get to each level. It's very hard to get to the 1.2 points. It's kind of like a bonus round thing. So Mubot will tell you your points, and then you can see what amount of bonus you have. Mubot will tell you that. Mubot, you awake, man? He's awake right there. So it is hard to get to the very, very top tier levels. Each level gets harder and harder to get to. So great job, Max, right there, already at the point. It gets harder and harder to get to each level, but you can get there. The 1.1 and 1.2 are like the bonus rounds. So you might eventually get there. I hope you do. It's just a harder and harder tier to get to each time. The earlier levels come really quickly. Maybe I might space them out even more a little bit next semester to figure out a good spacing. Just want it to last the whole semester, and I want about half the class I want most students to get to 1 point, and I want 25-30% to get to the max. Like that's like a super bonus. Does that make sense? and each one's harder. It's like I wanted to distinguish, like, I got to the top bonus. So, yep, keep hashtag show up. So last time we were talking about simple linear regression. When we're talking about simple linear regression, what are we talking about adding to our data? We're talking about we have data. Simple means 1, and we're using 1x, and we're doing what? Because we're going to have 1x, 1y. The simple part of it is the 1x. So specifically here, 1x. And so we're going to add a what to our data? I mean, it says it when you say simple linear regression. It's good to distinguish between simple linear and multiple linear. A line of best fit. Great job, Megan, right there. Excellent answers. Line of best fit. So that's the line of best fit. It's the one that goes through the data the best. And a big thing we did last class is we went through interpretations. We spent a lot of time, like 20, 30 minutes, talking about these interpretations right here. We didn't do that. Go back over here. We did the interpretations. So please go over these slides again right here and practice this. Once again, you should be able to do these interpretations without looking at the slides. I'm not going to look at the answers on the slide, but I'm going to interpret right here. Brian is currently highlighting the what right here. It's B0, which is our estimate of beta 0, but that is B0. I'm going to write the equation I generally use below this. This is y hat, predicted y value of B0 plus B1, and technically this is X1. That is the y-intercept. Great job right there. Wilton and David, excellent work. That's the y-intercept. So when we talk about the y-intercept, it's the value of what we expect x to be, the value of y when x is 0. So for individuals who have no experience, like prior work experience, we would expect their monthly salary to be $3,526 on average. You can see that's what it says right there. When we go over here and we do the slope, this is where people lose points on the test. It says it right there, but I'm going to read it without looking at it. 2 individuals who differ in their experience by 1 year are expected to differ in their monthly salary by $10.4, where the individual who has more experience is expected to make more money at the company. Practice that. Practice that. Well, that's my echo voice.
There's the new body.
So, once again, practice this. Be able to do it with any sort of coefficients we give you. It's not always people. Sometimes it could be tables at a restaurant. So, and it says bills right there, but that's a table at a restaurant where you give a bill. So this coefficient right here would be, once again, not looking at it, 2 bills at a restaurant that differ by their amount by $1 are expected to differ in their, is it tip percentage? I didn't see with the Y variable. Tip percentage by 0.23. And since this is negative, we would expect tables with higher bills to have a lower tip percentage on average. It is tip percentage. Practice this. Practice this. Be able to do it by looking at the coefficients. It's not always 2 individuals. And we did this last time, so this is just a review right here. Is the intercept meaningful? Well, as a waiter, sometimes you do give a bill of 0. So, but then can you really calculate the tip percentage? Well, then it would be incalculable. So some debate, and we don't have any data over there, which would be an extrapolation of the model. But use these right here to practice. 2 tables at a restaurant that differ in their party size by 1 individual are expected to differ in their tip percentage by 0.92, where the larger parties are expected to have a lower tip percentage. Who feels like they can do this? We did a lot of practice last time, and I can't make this more clear by using effects on my voice. This is where people lose points on the test. Because a lot of times, if we say interpret this, what are people going to say? We'll say interpret the slope, and what will people put that's a wrong answer? This is a review from last time where I'm trying to warn you, I will see people put this as their answer. The really bad wrong answer when we say interpret that number is this. What do people say when we say interpret the number? They'll just say what? Which is a very bad wrong answer. You lose all your points basically. Like I just tell my graders don't give any points. Sometimes I even grade these because I like to make sure that the wording's really exact or like clear. Not like it has to be perfect, but what's the really wrong answer? They just say the slope is this. Exactly right there, Max. Yep. They just say negative 0.92. Well, that's not interpreting. That's just what is the slope. And then the second tier wrong answer would be for each individual in the party, the tip will decrease by this. Exactly. And then they're going to say things like that right there. Like Wilton, great answer, great wrong answer right there. Causes. Yeah, never say cause, never say will. Cause and will are instant points off. And if you say for each 1 unit increase in party size, no. We're talking about two parties that differ in the individuals by one person are expected to differ in their tip percentage by this. So be very careful. Practice this. I can't make it more clear that this is where people are losing the points. So we're over here to the least squares criteria. It sounds a little bit weird. No worries right there, Weldon. When we talk about the least squares, this is what the line does for us. It actually creates the smallest sum of the squares. So when you think about what is a sum of a square, well, when we get a residual, what could you do to the residual to get a square? Just think right here, if this residual is 4 and this residual is -3, I think we mentioned this last time, so maybe a little bit of review. What could you do to turn that into a square? Decently drawn square. So how could you turn that into a square? What would you do to the residuals to turn them into a square? So the residual is the actual minus the predicted. It's just how far away something is from the line. Here's the actual, which is the dot, and that is 4 above. Here's the actual, which is the dot, and that is 3 below. So how could we turn the residuals into a square? Square it. That's it right there. Nathan, you got to just square the residuals. And then why would you square the residuals? If you square everything, we mentioned this last time, so it's good to review. Why do we square all the residuals? Well, if you sum up the residuals, they add to 0 because some residuals are above the line, some residuals are below the line, and the line of best fit goes through the center of the data. So if you just sum up positive and negative numbers, the way the line works is you would just get 0. It's a good theoretical thing to know. So we square them because if you square things, what will you get by squaring all of these? To cancel out the negatives, everything becomes positive. And then what could we do to this is a residual. That's just a residual right there. That's a residual squared. What could we do to these squared residuals to find out how much error there is? To find out how much error there is, we could take the residuals and square them. And then we could do what to the squared residuals? So this is just a residual, actual minus predicted, squared. That's a squared residual. And what could you do to the squared residual right here to find out the total amount of error? Sum them. This is the sum of the squares residual, the sum of the squared residuals. And we call this sometimes the sum of the squared error, and someone might put here an R for the residuals. The sum of the squared error, because this right here, let me make a point to it. The error right here is this. This is an error. It's how much our model is missing by. It's the sum of the squared error, also known as the sum of the squares of the residuals from our model. So sum of squared errors. So when we do this right here, we are trying to make guesses. What is our best guess at the true slope? Here's the true slope. What is our best guess at the true slope? When we estimate the true slope. And you want to see this in your output where it says like estimate. And so this is what your output looks like. Down here in your output, you will see estimate. This is where it's found in the output. I mean, I'll show it here in a second. So the estimate, that's the estimate of the intercept, and that's the estimate of the slope in notation. So whatever values are right here, those are the values, and you'll see the estimate of the true slope, beta 1, is B1. Just remember, beta and B, they go together. So where is this found in the R output? Let's go take a look. Head back over to the main screen. I have some work up earlier from this. Here we go. So we'll use this today right here. We're just making a model where we have height explained by weight. That's correct right there, because this is the Y variable. This is the X variable. I'm going to just move this back away, and we'll take this out of the way. So when we look at this model right here, we load in our data, we make our model, summarize, and can you tell me the coefficient of the slope? What is the coefficient of the slope? Do I have that wrong button on? What is the coefficient of the slope? Just what is the coefficient of the slope? Estimate of the coefficient. We don't know the true coefficient of the slope, but what is the estimate of the coefficient of the slope? Good thing we're identifying this output. What is the estimate of the coefficient of the slope? So go over there to the estimates. And then what is the estimate of the coefficient of the slope? Exactly, Max. It's going to be this right here. If we go to estimate and we go down, this is the estimate of the coefficient. Great job, Wilton, right there. Excellent work. So that is the estimate, and the estimate of the intercept is this. So we could write out the model right here. by simply saying height, and then we could take this, and then we could add to it this, and then we could put in the variable here for weight, and we could actually predict someone's height. Who wants me to predict your height? You have to tell me your weight and your height, though. Say, I weigh this if you want your height predicted. Only if you want your height predicted. Only if you want your height predicted. So say, I weigh this. You can say your weight. Like, I weigh 167 right now. Crazy to say. And then, so my predicted height, and we should maybe put predicted height. And my predicted height is 5'8". Nathan, you're right at where I'm at. I'm predicted to be 5'8". And let's put here actual height. My actual height is 75 inches. And so what if I do this? What is Brian finding right here? What has Brian found right now? 230 right there. So we could do that right there. What have I found right here? And so we'll see if it predicts Parker a little bit better. We'll make predictions for other people. What have we found right here? We found the residual because I took my actual height of 75 inches minus my predicted height, and that's my residual. The model underpredicts me. Does that make sense? The model is, I'm up here. The model is underpredicting me. So now we go to 230, and we put in weight for 230, and 6'2" is 74. And now so the model predicts you to be, oh, look at this. Residual is going to be like 0.8. The model actually predicted you really well right there. Model was nearly perfect for 135. You can tell us if it got you can tell us if you want if it was a good prediction. So we don't know, but it predicts you at 135 to be 5'6". It says you are expected to be 5'6" right here. So the model is just making predictions by solving this. Very surprised, I know, right? Just complete.
Wow.
A little shocked right there. But the model makes predictions right there, and it's just predicting, and then we can use the actual 5'9" or 190. So we go right here, 190. And then we run it. You are predicted to be this. Oh, you're actually going to have a negative residual because your actual minus your predicted, your residual is going to be negative 1.2, I believe. And there it is. Practice this right here. Wow. David, you're tall. David is 203. And right here, 78 inches. I think. Oh, there we go. And so that is your predicted height. 5'6", you're 5. Oh, you are 5'6". We got it perfectly. Residual of 0, basically. Then, so this is what our model is doing, and we can visualize it, and we can see where people are at. Quickest way to visualize your model is with Visualize Model right here. I think we did actually some of this yesterday in our office hours. Great thing to check out. I would be over here, and I am about where this person is. This person right here is somewhere close to where I'm at. 6'3" rather. 6'3". Where's our tall people at? No one's taller than Brian. Not allowed to be taller than Brian in this data set. Let me see right here. Taller than Brian. Is there really not? What? Someone taller than me in this data set. Yeah, there's a few people. Where are they at? Are they off the model? They're 305. Oh. Where are they? I don't know. That's weird. Well, I'll be. Cool. Something just seems odd about that. They should see those people. Is it not extending the model all the way out? Let me try this. Plot, height, weight. What the heck? Data equals survey 10. There we go. Okay, yeah. Is it not showing those people? Oh, I think it's just the way the axis looks. It's really hard to tell. Yeah, it's showing those people right there. It's the people at the very end. That person's at the very end. Are we seeing that person? Sometimes you don't get all the points. Ooh. What's going on right here? I'm going to look into this. Is it not plotting that one individual? It is. Is it? Maybe I'm just blind. 105? So then we could predict for 105. All this model is doing is making predictions, and then we can solve for the residual right here. 63. So you are predicted to be... oh, wow. Look at that. So what is your residual? Solve right now. Tell me the residual. You were predicted to be 64 inches. You're actually 63 inches. What is your residual? So what is your residual? Yeah, that's why maybe, 1 point is that. So it actual minus predicted. Let me double check right here. I think it's negative though, Max. I think it's negative because your actual height is 63. Yeah, it's going to be negative because you're actually plugging the numbers right here. 63 is your actual, 64 is the predicted. So make sure to the negative right there. So that means the model over predicted you. Does that make sense right here? The model over predicted you. Yeah, definitely, David. You'd be an outlier. So make sure to do, if it's negative, that means the model over predicted you. So we predict you to be 64 inches tall, but you're actually 63. So since you're below the model, does that make sense? You have a negative residual. Who gets the concept right here? Like you're predicted to be 64 inches. You are 63 inches. So you have a residual of -1. You are -1 below the model. So that's what we have going on right here. Very important to see that. You know what we could do with the residuals though, is we could take all the residuals pretty quickly for the model, and that's every residual. You know what you could do to those? You could square them, and you could sum them. And we've literally found the sum of the squared residuals for the model. And we can even check this by looking at the following. And this confirms we actually did it properly. More on that later. But notice right here the sum of the squared residuals. Who notices this? And who sees the sense this is making? The sum of the squared residuals. And then look at my code. The residuals, what did I do from the residuals from the model? I did what to them? What am I doing to my residuals from the model? Is the mean square error just the... Yes, the mean square error is going to be, because I think we have to square it, and then we're doing the, yep. And then we're going to take the root of that. You're on the right track right there. Yep, Max. And then we'll do the root mean squared error, because that brings it out of squared units, because we don't like squared units. Who sees this right here, that this is the residuals, and this is the sum of the squared error of the residuals? Does this make sense? Who understands how this number is being obtained right here? Very important for what we're going to be doing right here. Who sees that? Just want to make sure people see this. Like when you look at that up here, like, oh, this is the sum of the squared residuals. The model has residuals, how much people are missed by, and then we're going to take these residuals and we are going to square them, and then we're going to sum them. And this gives us the sum of the squared residuals, which we can find mathematically, or it's found via a lot of different code, but pretty easy to get there conceptual. And then we need to know where these estimates are in the model, which is what we were reviewing just a moment ago. Let's hop back to the notes. This slide, it's cool. Any test question written from this slide, I hate. We don't use these equations right here, but I do want to point something out. That one thing you'll notice right here is correlation is used to estimate B1. So what do we not want to see? Think back to your correlation. Correlation is ill estimated if the plot has what? So if the plot has what, we don't like the way correlation is estimated, which means we probably are not estimating the slope properly. What do we not want to see with correlation? Because if we're basing the slope of this line on correlation, which is probably the biggest conceptual thing to know, if the slope is based on correlation 0 would be bad, but when is correlation ill-estimated? Like a bad estimate? Like, I don't know if you should be doing correlation on that. Which one of these? Correlation is not estimated well when correlation has what issue? What issue can correlation have that would make correlation? Outliers are bad and heteroscedasticity. So if there's outliers, heteroscedastic. I don't even think in outliers, but yeah, just outliers. Heteroscedastic relationships, which you see on the right under the extra credit, are gonna be bad right there. Nonlinear is gonna also be a problem because we're fitting a line. So you can see right here the conditions come into play. More on hints for your assignment coming up a little bit later. So when we do statistical and practical significance, statistical significance is the easiest one. What is the least significant line you can think of? I want someone to think of a not significant line. What is the least significant line you can think of? What is the least significant line you can think of? A line with what? What is the least significant line you can think of? A line that's probably just completely by. What is the least significant line you can think of? The least significant relationship between X and Y, and a horizontal one exactly. That's going to be the least significant line. So what would be the p-value for this one right here? If it's the least significant, most likely by random chance, hint, most likely by random chance. If you had a slope of 0, then what would be the p-value for this? If you have a slope of 0, what would be the p-value? Good theoretical question right here. It'd be 1, yep, because this is the most likely. Think about p-value as the probability of getting our result or result more extreme by random chance. Well, if there is no slope, which is a classical assumption, we don't do the classical statistical test right here, but if you assume that the true slope is equal to 0, then observing a slope equal to 0, this just says the null states that the true slope is equal to 0. The alternative is that the true slope is not 0. The most likely thing to see here is a slope of 0. And observing that or something more extreme would happen 100% of the time if the slope is 0. That's the most likely result to see. And we don't do the classical statistical test, but we do need to understand that we are doing a test on the XY relationship, which is the slope. Just all of this right here repeats what I've said. So this is just a generation of random lines, and it's really cool to run. I'm going to go ahead and run this over here. We're just going to grab this code, and we're going to take it and plot the lines and run this a few times, and I want you to see something. When I run this code, and let's actually add a summary below this, I'm just going to run all this code right here and make a summary of the model after running it. All of these right here are going to create, and actually, you know what's funny? My first line right here is actually what? My first line is actually what? Now look at the slope and the significance of the slope. By complete and utter, my first line is what? My first line is actually this. Shocking. 42.72% of the variation, whatever y is explained by x. When x is equal to 0, we'd expect y to be 9.35 on average. There is no x and y context right here. Two individuals who differ in x by 1 unit, or if they're individuals, are expected to differ in y by 0.47 units, where the individual with the higher x is expected to have a lower y. Practice those interpretations. The relationship between x and y is actually this, just barely. The relationship between x and y is actually this. Do not look at the intercept. No one cares about the intercept. The relationship between x and y is actually this. And it's by random chance. It is actually statistically significant. Sometimes you get a low p-value by random chance. Type 1 error. But watch this. Let's do it again. Oh my gosh. Lightning struck twice in a row. Now, the probability of this happening after the first time was 1 out of 20. The probability of it happening again or 2 times in a row is 1 out of 400. But it did, because 20 times 20 is 400. We did actually get a second p-value below 0.05. Oh. Now, the probability of it happening again is 1 out of 20. But it didn't. What do you notice about this? It looks rigged, right? I should have set a seed and I didn't set a seed before this, I promise. What do you notice? Because then I could control the randomness. What do you notice about this line and this p-value, which is the concept we were going through? What do you notice about this line and this p-value right here? Take a look at this line and tell me about, oh, that line looks a lot more this, Brian, and your p-value is a lot more this right now. Here's the statistical significance. Here's the line in the background. Brian, that line looks a lot more this, and since it's a lot more this, the p-value is going to be a lot more this. So this line right here is a lot wider. It's a higher p-value. The line is flatter because there's a weaker relationship. And that one, oh, I thought we actually got another one. You see, when the line is flatter, we'll try to, ooh, it's a really flat line, really high p-value. And you can, there's another statistically significant one by random chance. We're actually getting a lot of close to statistical significance. Once again, this line almost looks perfectly horizontal, and this p-value is very close to what? And look at the coefficient. The coefficient was basically 0, and the p-value is basically what? This was the concept we talked about earlier, and Nathan, 100 points, is getting it right there, explaining, yep, the p-value is basically 1, and the less, if the line was steeper, like we saw in our earlier examples, if we go back here to this model, and we visualize it now, you can see a p-value that this is 0, basically. If you're wondering what that is, this p-value right here is the following. There it is right there. That is the p-value you're seeing. It's a ridiculously tiny value that R is just showing you with scientific notation. This basically means your model is super significant because this would not happen by random chance. Are outliers an issue here? Yeah, probably. But I don't know. Works-ish. So this is what we're getting by random chance. You could get something extreme. And here we are with the sum of the squared error. With the sum of the squared error, we have 2 sums of squared errors. And this is the important one that we're now talking about. We have what is called the naive model. And please take a note. Where is the naive model on Y? The naive model does not use X at all. It only uses the what of Y, and there's the notation for it from Stat 201. The naive model for 50 points only uses the what of Y to explain the Y variable. So it just makes predictions for everything based on the this of Y. So the naive model only uses the this of Y to predict for everybody. The average right there, amazing answer. It only uses the average. So now you could calculate a squared error from the average. What do you notice about the squared error from the naive versus the squared error from the model? What do you notice about the squared error from the naive versus the squared error from the model? So what do you notice about the squared error from the naive, which you can see visually is going to look water from the squared error? Oh my gosh, that's bad right there. That's not good. We don't want big squared errors. So I'd have to draw all these squares and then add them up. The computer will do this for us. Naive has way more error because it's not using X to explain Y. The naive uses the mean of Y, and then it sees how far away each point is. It calculates a residual, squares that residual, sums up the squares of the residuals, and you have the sums of the squared error from the naive. Great answers right there. So the naive is like a starting off point. You know what we want to do? What do you think we want our model's error to be? What would you like this to be right here? And I'll show you visually what it would be. What would you like your model's sums of squared error to be? 0. And if this is 0, what value will become 100% or 1? Because the error is the variation. And now it looks like we've explained all the variation. So if there's no error, our model's perfect. It explains everything. Close, because it could look like, I'll draw a quick sketch. It could look like this. It could look like that. Not R, you're super close. You're super close. That would have an R of 1. That does have an R of 1, but the top one has an R of -1. R squared, Wilton, yes, nice job, Wilton. This will have an R squared, which is percent of variation explained. The naive tells us how much variation there is, and then this right here, I want to point to it. This right here is how much variation we have what right now, which we want this to be 0. The naive tells us the amount of variation there is, and then the sums of squared error for our model tells us how much variation we have what. Because this is how much variation there is. This is telling us how much variation we have what. And you'll see the equation here in a second for R squared. So this is how much variation there is. It's just how much error there is. Ah, you're close, Megan. So this is what we haven't explained, hence why we want it to be 0. But Megan, that's worth 100 points too. This is the unexplained, and then we can subtract to figure out, and it's explaining it right here. I'll show the equation. I'll go through the theory, but where is that? Here it is. We can subtract to get the reduction. This is the reduction. What you have right here, I'm going to write over for a second so you can see. This is the naive error. So let's put the naive right here. The naive is the total variation, and the total variation is taken from the distance a point is away from the mean of Y. That's the naive. And then this over here is our model. You would like the model to have an error of what? What would you like the model to have an error of? Once again, you want your model to have what error? Just think this portion right here, you want your model to have what error when you make a model? You'd like your model to have what error? And then I want you to solve this. And if your model has no error, your model makes no errors, it's perfect. I'll give you a hint, this will help with it. We compare the reduction to the naive. What do you get? What does this mathematically solve out to now? Because if you say your model has no error, then what do you get when you solve this equation now? Do you see it? Then it's naive over naive, so it's the total you've explained all the variation. So the reduction is how much of the variation we've explained. So our model is the unexplained variation, which you want it's weird to say your model's the unexplained variation, but it's the leftover, the residuals. So that's the second part right there is the error from the residuals. So maybe it'll make more sense if I call it residuals. People call it model a lot of times. So if you see model, it's your residuals. Like the error from your model, which is the residuals. So, but you want your residuals to be 0. So if your residuals are 0, then there's no error left, and you have an R-squared of 1, and you've explained all the variation. So think about this when you hear about stat 201, you're saying the percent of variation we've explained, and it's starting off by comparing it to the variation that exists, which is calculated from the what. How do we calculate the variation that exists in data? We calculate the variation that exists in data by calculating the variation from the what, the error from the what. How do we calculate the variation that exists in data to begin with? How do we calculate the variation that exists in data to begin with? What is our jumping off for calculating? It's on the screen right here. What is our jumping off point for calculating the variation that exists? Oh, no. I got a question follow-up if I'm right. What is our jumping off point for calculating the variation? Correct. David, you're right there. Calculating from the naive, which is the mean. So you are correct. When you say the mean, you're saying calculating from the mean, which is the naive model. So it's called the naive model. But let me ask you this. Who knows what R-squared is right here? And it'd be the residuals from the naive. Who knows what R-squared is right here? Take a moment. I love to ask questions like this. Who knows what R-squared is here for 50 points? What is R-squared? So what is R-squared right here? Who can calculate the R-squared of this? So here the screen. Take a moment to calculate R-squared. Can you do it? Can you calculate R-squared on this? I think you're right, David. Because we take the total variation that exists, and then we did not explain 174. That's what's left over. Our model did not account for that, because that's what's left in the residuals. And that is what we have explained. This is also called the reduction. Listen to the keywords right here. This is how much we've reduced it by. 1,264 to 174 has been reduced by 1,090. So now we take the reduction and divide by the total to figure out how much of the total variation we have explained, which is 86.2. The point is we want to understand the reduction and how much of the variation we have explained. Great practice right there to understand the concepts of how we're mathematically getting R-squared right here. So we'd really like our regression model to have no error. And we're trying to figure out if this reduction is statistically significant, likely by random chance. So what is the smallest possible reduction? And we saw it with some models earlier. What is the smallest possible reduction? 0, it says the data, yeah, if it fits better, there it is. I was worried. If it will always fit, so it has more flexibility, the regression model will always fit better, unless they're completely by random chance. Even when X and Y are unrelated. I want to look into this. So what we'll see here is that the SSE, so R-squared is the percent of error explained, yes, calculated from the naive model, the percent of variation. So it is error, that's variation right there, which is calculated by the sum of squares. Is that making sense, Nathan? I want to slow down when people especially ask the big concept questions. We calculate how much variation exists from the naive model, and then we see how much variation our model accounts for. So we're trying to see how much we reduce the variation by. That makes sense? Awesome. We're trying to see a large reduction in the variation, which means we want the residuals for our model to be what? We want our model to have very small residuals. That's all right. I was wondering what that was. I was like, is that code? So here we are looking at just a simulation of it. And what do you notice about the random chance permutations? The reductions for the random chance permutations are probably going to be close to what? The reductions for the random chance permutations about random permutations of our data are probably going to be closer to what for how much they reduce the error from the naive model. They'll be closer to this. By random chance, we'd expect reductions closer to what? By random chance, we'd expect a reduction in the sums of squared error because it's just by random chance. X and Y are not related if we permutate them. So by random chance permutations, we'd expect reductions in sums of squared error closer to this. By random chance permutations, we'd expect reductions closer to 0. We observe a reduction of 21.3. Take a moment right here, calculate the R-squared. Who knows the R squared right here? A lot of numbers on the screen. See if you can calculate R squared. It can be done pretty quickly for this example. See if you remember how to do R squared and see if you can calculate it. Find R squared. Here's a hint. Your model looks pretty good. Your model looks to fit the data really well. There is a little bit of non-linearity to it. All models are good. All models are wrong. Some are useful. Messed up the George Box code. Wilton, I think you have it reversed. That was a hint right. Wilton right there, 100 points. I think you have it reversed, Wilton. You used the regression error. We want to look at the reduction, so you might have done 1 minus the... Does that make sense? So the R squared right here, look at the model. The model's pretty good. That's a really good model right there. So just visually having seen a lot of models, we're going to take the reduction, which is what we want. We want to reduce it and divide by 23.3, and then we get the R squared. No worries, Wilton. Hey, Wilton, this practice... Whitson right there. Sorry, Whitson. Practice right there. Practice makes perfect, and it gets you extra credit. This is the error our model has, which is how far away these points are away, summed and squared. This is the error related to the naive model, and this is the reduction between the two. We want a reduction. Reduction is good. We're saying we reduce the error. And I just want to say thank you for everyone following along right now. The more you practice these, the better you get. Wilton got it right. Sorry, it's in Wilton. So we see right here some reductions, and I want you to tell me, what do you think we have right over here if we look at the probability of getting a reduction as extreme or more extreme than ours? What do you think we're looking at if we're looking at a reduction as extreme or more extreme, which seems highly unlikely by random chance? So we're looking at the reduction in SSE achieved that we got. The green line is our reduction. All the results in here are random permutations, not the green line included, not the green line. So these are random permutations, just random chance, which you notice there's a lot near 0. So that red area would be the what? It's highlighted up there. Does it say it? Oh, it doesn't say it. We should know that the probability of a result as extreme or more extreme than our result occurring by random chance variation is the what. So the red number I've circled, the 2%, which is an estimate of the what for obtaining our result by random chance. We have our reduction. Stands for the sum of the squared error. It's the p-value, and this is the p-value right here. So it's the sum of the squared error, and I'll just show that again really quickly. So I'm going to zoom back to it. Visually speaking, we are taking these errors. So there it is right there. There's an error, and we're squaring it, and we're summing it. So the SSE stands for the sum of the squared error. Max, thank you for asking that right there. It's the sum of the squared error, and the error is a residual. But we can also do a sum of squared error from the naive model, and we can also do a sum of squared error from the regression model. Notice how these have the subscript, where you could be doing the squared error from the naive, or you could be doing the squared error from a regression, and the regression has a much smaller squared error. So it's the subscript tells us which sum of squared error we are using, if it's a sum of squared error from the regression or a sums of squared error from the naive. And then we want there to be the regression having a very small. This one we want to be small, and the first one is just inherent variation in the data. Like, does the data have a lot of variation from the mean? So this one doesn't really matter how large or small it is. We just want this one to be way smaller. We'd love for it to be 0, because if it's 0, we obtain an R squared of 1. So the less the unexplained variation in a correlation, then the higher the R squared, and the more the data is explained by the model. I believe so. The less the unexplained variation, because this is the unexplained. This is the error from the model right here. So the less the unexplained variation, which this is good, a correlation, then we will see higher correlations, because then R squared and correlation are associated. And the more the data is explained by the model, exactly, because then the model will be explained because it's reduced the amount of total variation. Yep, David, that's excellent work right there. Great job. That's correct. And R squared and R are related. Like, you can obtain R from R squared. Be careful when you square root it to look at the direction. This is just going through some of the output right here, but I do want to mention a huge thing for your assignment is we have these key assumptions. So someone already mentioned, I think on the Discord, they were asking about this. What do these assumptions mean? So this assumption has 3 parts, and the 3 parts of this are wondering about the residuals. So when you look at the residuals right here, the residuals are notated as E, but epsilon stands for the true. So we call our residuals E, but the epsilon right here is called a disturbance. It's just the true residual. I don't worry too much. I don't go over much theory on that. But If we were to say we knew all the data, then we would say we have the disturbances. If we're using a sample, we would say we have the residual. Does that make sense on the difference to everyone here between epsilon and E? E is when you have sample statistics. Like if you're talking about your sample model, you'd be calculating residuals right here from the sample statistics. But if you had the true model, you would have disturbances from the true model. So if you were talking in true sense, like I have all the data, so now there's a disturbance from the model. This is called a disturbance. But if you're saying I have sample results, then you'd say I'm calculating a residual, which is how much my model misses by. In any event, both of these are how much your model misses by, whether you're talking sample statistics or population parameters. I'm lucky somehow I'm able to write that right there. I don't know how. My handwriting is horrible. But the terminology is not so important. You can still just think about these as residuals. And I want to point out they have 3 conditions. And let's talk about them over here on the main screen. So these 3 conditions are super important. And look, we have regression right here. Well, you know what? Let's just take this 201 problem and look at this. We got some 201 right here. All we need to do to make it 320 is just go over here and do this. So am I talking about residuals or disturbances right now for 50 points? Look at the equation as we normally do. I'm going to talk about what. Like if I have a point right here, since I'm using estimates, what is going to be how much I miss by? How much I miss by right here would be known as the what? That's a residual. Exactly. That's a residual because it's just the estimates. If we have the true model, which we really never use, it's disturbances, which is an assumption about what we're assuming right here. We're assuming if this is like towards the true model, then the disturbances will look like this. The first condition was that the residuals are like this. How does that look if good or bad? So we're going to go over all conditions right here and how it looks if it's good or bad. So the first condition is normally distributed. We'll draw it good on the top and bad on the bottom. So normally distributed. So that stands for normally distributed, which means if it's good, we'll draw a bad one on the bottom here. We should see 68% of the points around the center, 95% of the points within 2 standard deviations, and then 99.7 within 3 standard deviations. What we don't want to see is where we have points that suddenly jump out right here like this. It's probably most allocated to outliers, but we want to see that the residuals have a normal pattern. And it's pretty easy to check, and we'll see this in later assignments, with a function we have called check regression. You can go here and use check regression, and I want you to just say this. What do you think check regression does for you? This is a huge help for later. Like, this is huge. What do you think check regression does? What do you think it's going to do for you? What do you think check regression is going to do for you? Oh my gosh, look at what it says. It says it checks something over here. What's it going to check? Oh my gosh, we were just talking about that. It's going to check quite a few things. And it's going to check the regression for the conditions right here, which are important.
Wow.
Let's check that regression. And look right here. What do you see we have? We have a histogram. But do we look at histograms or do we not look at histograms? What do we look at? What do you think we look at? Do we look at histograms or do we not look at histograms? Because a histogram can tell us if it's normal. But do we look at histograms or not look at histograms? We look at that QQ plot. Good review from earlier. QQ plot is looked to no histograms right there. Do not. That's 100 points. Never look at that histogram. You know what we're talking about. So how does this QQ plot look? Bad or good? How does this QQ plot look for our residuals having a normal pattern? How does our residual plot look here for it having a normal pattern? Does it look good or bad? Does it look good or bad for having a normal pattern? Good or bad? The red line indicates normality. So what are you thinking? Good or bad? It looks pretty bad, especially down here. We got some problems with normality. And if we did a statistical test, I'm preparing us for later, we'd actually fail the statistical test. More on this when we get to this chapter, but this is how we can actually test the conditions. The next condition, so this one might have problems. Go back in time, might not be able to go far enough back. Oh my gosh, we went far enough back in time. The next condition right here is that it has a mean of 0. And this one's sneaky. This is a sneaky condition right here because the mean of 0 is basically this right here. And the mean of 0 is actually seeing if we meet what? Here's where it's not met, where the line where we don't have a mean of 0, where there's not a constant mean of 0. So what do you think the mean of 0 is actually testing? What do you think the mean of 0 is testing? That the line right here has a mean of 0, as in like there is a 0 residual at all times. Like if you look right here, the residual would be 0, but residual looks negative. Like the mean residual at any point is 0. The mean residual here looks to be 0. Like the residuals in here look to go to the line, which is 0, because that's when you have residual 0 is when, we see things would average to 0 there. Doesn't look to be averaging to 0 here. It looks like there's a positive residual here, 0 residual. That's good. 0 residual. It's on the line. So what is this testing right here by having a mean of 0? Like the residual is usually around 0. Like if you average around at any point, you would see about 0 there, but you don't see about 0 there. That's bad. You would see about 0 here. That's good. You don't see about 0 there. Funny enough, you do see about 0 here, but you don't see it other places. It's linearity. So the mean of 0, it's Wilton right there. Sorry. Wilton, you're exactly right. This is the linearity, because we want the line to pass through the middle of the data. Like it should be around, the points should be around it. It shouldn't curve around it, and the residual should not have a different mean. We want it to have a mean of 0, so that 0 right there is actually the linearity condition. And take a look. You actually have a test for the linearity, and do we pass the linearity? I think I highlighted the wrong one for the normality. Do we pass the linearity for this model, or do we fail it? I'll give you a hint. We fail it. These low p-values are actually bad. More on that in a later chapter. But once again, we have that test of linearity. I bet you can't tell what the last one's going to be a test for. So let's go ahead and look at that last condition right here, written out in notation with a sigma right here. And I want to point with what's going on with sigma. The sigma is one value. So when you put sigma here at one value, that means the spread is going to be what? If it's one value, use a C word, the spread is going to be what throughout the model? The model is going to have a what spread if we give it one value for the spread. If there's one value for the spread will be what throughout the model? It'll be consistent, constant. So it's going to be one constant value. And you could probably just call that the spread is what throughout the model. Like you could probably say, well, that means the spread is what throughout the model? You could say the spread is this throughout the model. Well, it's consistent, it's constant, it's a blank spread throughout the model. It's homoscedastic, equal spread. Do you see it? It's right there. The condition is right there. That's the equal spread. And this is homoscedastic equal spread. And it's important to see these things and then connect the dots and be like, okay, this is the equal spread test, which we are doing by looking at these different conditions, which are notated right here for our assumptions. Here we have the normality of the residuals. Here we have that there is constant, like a linear, the line goes through the middle of the data. And here we have a constant equal spread, which are our 3 ways we can check the regression later on when we look at this in simple regression part 2. It's a good way to make sure you connect the topics. That equation you're looking at there checks the normality, the capital N, checks the linearity with the mean of 0 throughout the model, and the equal spread. And this one actually fails all the conditions. Later on, we'll talk about that. Let's hop back to the notes. Probably one of the easiest things for us to understand about our model is whether or not it is statistically significant. Is our model statistically significant? We will look at the p-value of the what. So think about this. What matters here? This or this? To tell if your model is statistically significant, you want to look at the p-value of the what. We're actually looking at the reduction in the sums of squared error, but it can be viewed by looking at the what. The p-value of the what can tell us if our model is statistically significant. You don't want to look at this. The slope right there. The slope is going to be where we look for statistical significance. And we'll see that right here, that the model's significance, which can also be found via the ANOVA, is when we look at the reduction, which is going to be right. My brain's breaking for half a second. This is the error, and thus this is the reduction. Let me write some notes on this. This is a good number. We want this number. I'm going to ask a tougher question right here, and it's important to know how to read the important things in this output. We don't do a lot of ANOVA table stuff in this class, but I want you to know what's important right here. This right here is the reduction. This is the residuals. Question 1. What is the total error your model makes? What is the total error your model makes? So if we have the reduction and we have the residuals. And I'll write an equation for you. So total equals, or let's put naive, which is the total. Try to solve this out as I'm solving it. The naive, which is the total error our model makes, is equal to how much we've reduced it by, reduction, plus how much is left over in the residuals. So what is the total error your model makes right here? So what is the total error your model made? Like starting off with the naive, what is the total amount of variation that exists? And I'm going to ask him a tougher question here. Good practice knowing how to read this table. This is just telling you the error. What's right here? This is the reduction. This is what's left over in your residuals. That's what you have not explained. So it's a good way to think about it like this. Is the total is equal to what is unexplained plus what is explained. So this is what is explained. This is what's unexplained. You either explain something or do not explain something. So what is the total variation that exists? What is the total variation that exists? Great job right there. So David's adding the numbers together. Excellent work, David. 100 points right there. That's the total variation that exists. So what's R squared? Can you calculate R squared from this? Very fair question on the test. Calculate R squared from this. Take a moment to see if you can calculate R squared from this. I'll give you a hint. And use Brian's notes to help out. I'm kind of helping out a lot by doing this. So you want to add them to find the total. Because you either explain something or don't explain something. So the total that there was adding them together. Did I do a minus? No, it's a plus. Good. So you want to add them together because you either explain variation or you don't explain variation from what exists. So here's the variation that exists. Your model will either explain it or not explain it. Yep. You are correct. Great job right there, Max. Max earning everyone another 50 points. So Max divided this by the total of what exists. So we just do that right there to find right there. Great job practicing. Great job. Because that's how much you explained out of the total. Does that make sense? Like we explained 17% of the variation out of what total exists. So if you sum these up, you will get the total. And then you divide 33.4 million by the total. You get what you explained out of the total, which is the R squared. Very important to see those things. You never know what's going to be on the test. So there's the calculations showing the table and explaining a little more in detail. We don't really focus on anything. So expected divided, explained. Sorry, that's explained right here. This is, I didn't have enough room to write it. This is the explained or what your model accounts for, which is also the reduction. So I'm going to write a few words up here for what this could be called. This is the reduction. So I'm going to circle it. This is the reduction, which is good. We like that. The reduction means we've explained it. And I used another word. So say we've reduced it by this much, it means we've explained this much variation. The other is the unexplained. Does that make sense right there, Mon? Thank you for those questions. That's how much we've reduced it by, and that's the explained portion of the variation. The other one is the unexplained, which is in the residuals, because residuals are bad. We don't like residuals. What would you like your residuals to be? Quick, easy question for 100 points. What would you like the residuals to be? You would like the residuals to have a sum of squared error of what? You would like the residuals to have a sum of squared error of what? Of 0. And then you've explained all the variation, because then you've reduced everything that existed, because the total of this would just, yeah, good stuff right there. We've gone through this output a lot. I went through it in detail last class, going through each portion. So check out last class if you want to review how to read this output. But I want to point something out again and again and again. The significance in the simple world of your model is the significance of the slope. That ANOVA that was run previously does give you an F statistic telling us that the reduction we observe in the sums of squared error is 18.6 times more than we would have expected by random chance. We can write our regression equation right here. We are predicting salary, and salary predicted would be equal to, I'm going to abbreviate these, 3228 plus 85, I'm abbreviating, times education right here. Now, is this statistically significant? It's yes. It is, because the p-value for the model, which we have circled right there, I'm going to try to highlight them, is below 0.05. It's below 0.05, indicating to us statistical significance. What you'll look at right here and see is that the standard error is a measure of uncertainty. Notice how when you divide the standard error by the estimate by the standard error, you get the t-statistic. So dividing these numbers right here give you the t-statistic. You want a very, very what t-statistic? You want, and look at those t-statistics. If the t-statistic is larger, the p-value will be whatter. Good things to know theory-wise. We want large t-statistics because that'll mean there's a large estimate, especially for the slope. Large in magnitude, exactly. So you want small uncertainty, which standard errors are uncertainty, and we want a larger estimate. We went through this in more detail last class, so check it out. What is the RMSE? I think we have 2 more topics today. The RMSE is the root mean squared error. And here's a huge hint for your assignment. It is the typical miss we make when making predictions. The typical miss I make when predicting somebody's salary is about $433.4. The typical miss I make when predicting somebody's salary is about $433.4. Do not say we will miss by this. This is just like on average we miss by this when predicting someone's salary. It's in units of the Y. It's not a percent. I typically miss predicting people's monthly salary by about $433.4. I want you to think what the RMSE means, though. The RMSE, also known as residual standard error or uncertainty in the residuals, is the root mean squared error. What do you notice cancels right here? What cancels between this? Important to see this. When I saw this, I was like, oh. What cancels between root mean squared error, which is RMSE, the root mean squared error? Root and squared, what are you left with? You're left with mean error. Why don't we just do mean error? Why not just do mean error? Just let's take the mean error the model makes. What's the problem with just taking the mean error? Exactly, Max, you're seeing it. Because we square it because you can't just do the mean error because you'd get 0. Why don't we just call it? Because if it was mean error, then they'd all be 0. Because there's positives and negatives. So if you do the mean error is always 0 because the line goes through the center of the data. So you square it so they all become positive numbers. And then you root it to bring it back to units of the problem. Because you could do mean squared error. Some people look at that. But that's in squared units. So then you typically miss by this much squared units. So the rooting brings back to the units of the problem. Root mean square error will always be a positive number, indicating you miss by about this much off of it. Like it's a plus or minus. Not saying you will miss by that much, but it's like an uncertainty of how far your model misses by. So it's just taking your errors, squaring them to make them all positive, finding out the average, and then rooting that to bring it back to the units of the problem. So good stuff right there. What is the RMSE right here? We just said it. Typically, I miss predicting somebody's salary of about by 433.4 units. So not bad right there. More context of RMSEs, and we talked about R squared. So like I said, we're doing great today. And there's more R squared. Now, how do we interpret R squared? R squared is the percent of variation in Y explained by the variation in X. Blank percent of the variation in Y. I'm going to type in the chat. Blank percent of the variation in Y is explained by the variation in X. So if you have an RMSE of 5 units, would it be able to tell us that the 5 units? It would just say you typically miss by about 5, but it's not for one prediction. It's on average for your model. Like, because think we're taking the mean right here. So it's on average, our model typically misses by about 5 units. Is that good or bad? If you were to be able to predict a baseball team's win-losses and you were off by about 5 wins, would that be pretty good for a baseball team in a season? If you could predict within about 5 wins, like I'm typically off by about 5 wins when I predict for a baseball team how many wins they'll get. If this said 5 right here, would that be pretty good for predicting baseball seasons? I'm typically off by about 5 wins for how many wins the Braves will have this year. Typically, I'm usually off by about 5 wins when I predict the wins for a baseball team. If you didn't know, baseball seasons have like 162 games or something. So if you're off by about 5 wins, that'd be pretty good. You'd be making pretty good predictions. How about if we predict for a football team? When I'm predicting how well UT will do, I'm typically off by about 5 wins. Well, 5 wins, if your team gets 7 wins, that's you're probably UT. Sorry, UT. If your team gets 12 wins, you might be Alabama or something. So if you're off by about 5 wins for a football team, that's horrible. So what matters right here when we're talking about the RMSE is the context. And this is a matter of practical significance. This is practical significance. Huge hints right here. This is practical significance along with what other concept is practical significance. What other concept, RMSE, and what else will give us practical significance right here? RMSE and what else gives us practical significance? Make sure you know this. RMSE and what else gives us practical significance? RMSE and what else can be used in linear models to look at practical significance? RMSE and R squared. Both of those are used for practical significance because I can tell 37% of the variation in the response rate to the census is explained by the percent of people who rent. And that's what we see right here. We just say the Y variable, blank percent of the variation Y is explained by the variation X. You can see right here different R squareds. If you know somebody's experience, knowing somebody's experience only gets you about 2% of the way, or about 2% of the variation in somebody's salary is explained by their experience. What was the number one most important thing right here for understanding the variation in somebody's salary? To best understand the variation in somebody's salary. Oh, I highlighted the wrong one. Don't look at the adjusted yet. That's an error. About 3%. What was the best variable for understanding the variation in somebody's salary? What was the best variable that gets you the most way to understanding? And it's under the multiple R squared. So that's just R squared right there. The best variable was education. Knowing the variation in people's education gets you about 17% of the way to understanding the variation in their salary. Or blank percent, 17% of the variation in salary is explained by the variation in education. Huge hints for your assignment. This right here, it is very, very, very statistically significant. Here's the p-value. But what do you notice about the R squared? Not so good. So this is probably not practically significant, even though, want to point it out again, super statistically significant, probably not so practically significant, because we only understand about 1% of the variation. We have some huge misses in here down here. Now the F-test. Does it matter which way we phrase it on the homework? It's always blank percent. Oh, between the gets you. Tell me if you think the graders are mean. It shouldn't matter. Graders should be nice, but sometimes the graders don't know that there's 2 ways. There's a lot of ways, but 2, I would say, good ways that we know of right there. So when we look at the F-test, the F-test is always a what over a what. Anytime you see an F-test, help me out right here. An F-test is always going to be a what over a what. We already talked about it earlier on this semester. It's always going to be a what over a what. What will the F-test be? An observed over what we would have by random chance. Yep, O over E. Observed over expected. So it's going to be what we observe in our reduction in the sums of squared error over what we would have expected by random chance. So what F's are small? What F's are kind of expected? If you were to observe something you were to expect, a very small F would be equal to what? Now, it's weird to get an F of 0. You would just observe no variation being explained. But what are F's that are pretty small that are like, yeah, I expected that? Because think if this was the expected, then what would F equal? If you were to get the expected, it'd be 1. So you're just saying, well, that's what I expected. So that's not a very large F right there. And I'm trying to think if this assignment covers this, because there's definitely no way we're getting through this today. We've got 1 minute. Let's go look at one model right here. I don't think the assignment covers this. Take a look at the assignment later. We'll make sure the assignment is not going over how to do the inferences right here. I'll make sure we covered everything. And we got 1 minute, just barely. Let's go look at one last model to finish off class right here. Let's hop into it. Now, something you must know is you must know the formula to make a regression. What is the formula to make a regression? Who knows the formula to make a regression? Put it in the chat right here as Brian loads up survey 10 data. And we notice here, I need to store my model into something. And so what is the formula? So we have to write the formula format. What do we do here? I want to maybe predict someone's GPA from their weight. So what are we going to write? Use the formula format. Blank tilde blank, comma blank equals blank. Even force any. Yes, great job right there, Veda and Ari. Y tilde x comma data equals. So we're going to go here and go GPA, height, data equals, survey 10. And now we're going to look at the model by going to summary of our model. And look, there's a statistically significant relationship between somebody's height and their GPA. Let's visualize that model. There's our visual. Really weird looking visual. There's the visual. Redo it to get the box out of the way. And what about this? If I were to add in gender and do a multiple regression, now it's no longer statistically significant. Gender was the lurking variable. We can even visualize this model, but this is multiple regression now. More on this later as we start to do multiple regression. That was multiple regression to end. So if you can't tell, simple regression is the backbone of multiple regression. I was able to do a multiple regression with indicator variables very quickly. Just wanted to show an example right there. And you can see right here, the statistical significance of height is no longer there because the lurking variable here was gender. The model is still statistically significant. Same spot for model significance in the multiple world as the slope was, since we had one variable in the simple world. Here's simple regression. And here's a multiple regression. Multiple just means multiple x's, kind of a peek into the future at the end of class. Great job, everybody. We covered a lot of material today. I think we've covered everything on the assignment. I'll double check to make sure we've covered everything. But there was, I know there's interpretation on the assignment with the RMSE and the R squared. I'll double, triple check. And if not, we might do some bonus. But if we didn't, let me know. How's everyone doing in the chat? Chat gets quiet here at the end. Everyone probably clicked off the video and said, I'm out. If someone said absolute error, is that the same as our, mean absolute error, no, you might be talking about, you're talking about MAE. MAE, my brain broke. Mean absolute error is MAE, which is a great point. So I think under library metrics, which is not hard to calculate mean absolute error, the mean absolute error is a different way of doing it. Ready for full break? Me too. To do mean absolute error, we just take the absolute value of the error. So we go to the residuals. Because now we can make them all positive. Here's the residuals by going here and going to the ABS, which is absolute. So there's the absolute value, and then here's the mean. There's debates among statisticians about which to use. The RMSE, which is going to square them, is going to give a bigger impact to large outliers, where the mean absolute error is not going to take as strong of impact from outliers. Oh, awesome, Benson. So good to see you here. Where do we find the standard error of the slope? Aha. Where is the standard error of the slope? Where is the standard error of the slope right here? And that is just our measure of uncertainty. Remember, we talked about that a lot last class. Where is the standard? Oh, we got a multiple regression. Go away, multiple. Where is the standard error of the slope? Can you quote for me the standard error of the slope right here? And that's our measure of uncertainty in our estimate of the slope. So where's the standard error of the slope right here? Yep. You got it, Wilton. Don't worry, good question right here. So to help out with that question a little bit right here, this is how much uncertainty we would have in our estimate for the coefficient of the slope variable. So relative to the negative 0.019, it's a little bit small. We want as little uncertainty as possible. And we covered that a lot last time. But this is our measure of uncertainty in the estimate of the coefficient of the slope. Like, it's how uncertain we are. We don't want to be uncertain. And to get the t statistic, which we talked about a little bit this time too and last time, we just divide by the uncertainty and we get the t statistic right here. And we want the t statistic to be large. There's a site that tracks NFL models, and I never knew that the mean squared error, if they do, so mean square error is good, and then that's in squared units. The absolute error, and then the mean, that's so, well, Max right there, excellent work. They're just taking and figuring out, probably MAE is much more popular. This right here, let me run the model again. MAE, and we'll just store this into MAE. That's the mean absolute error right there. So that's the mean absolute error, and I think library metrics can calculate these for you. Metrics. Okay. There's model. Ooh, I think it's model metrics. Computes the average absolute difference between two numeric vectors. Okay. So we want to go here into, we are predicting GPA. So here's the actual value of GPA. And then the second argument is the predicted. So we have to get the predicteds out of the model, which you can just go here and go to predict model. And there's the MAE. Yep, look at that. So I think it's about as much work to get MAE, but the function MAE will get you that. But what's great is you can also use these functions. They have a lot of different stuff. There's many, many different model metrics. Yeah, let's do that. Let's do that tomorrow. You can do MAE. We should have, there's MAE. You can do RMSE. There's RMSE, root mean square error. Oh, was there a different one? There's MAP, mean absolute percent error. I do not know MAPK. Computes the mean average precision. This is percent error difference. For a set of predictions in the context of information. Oh, never used that one. I've never used MAPK. Then there's mean absolute percent scaled error. Mean absolute. Well, let's look at metrics. There's a mean absolute percent scaled error or something. Go. Mean absolute scaled error. I think that's it right there. And so that's the computes the mean absolute scaled error. So that's going to take out some outliers. This function is only intended for time series data. Oh, yeah, no wonder I was doing time series. Mean, which one's this? That's a nice function. MSLE. Computes the average of squared log error. So that's going to take out some outliers. And yeah, the ones we want right there. RMSE, RMSLE. Let me see what RMSLE is. Computes the root mean squared log error. So root mean squared log error. I'm just fascinated by this. Computes the root relative squared error between. It's just statisticians got so many things they want. Sure. Here's different metrics you can get right there. We get an infinity on the MAPE. Oh, because do we have errors close to 0? We might. Let me store the errors. So we want the residuals of our model. And yeah, I think so. And want to view them. Okay, let's go back. It's sad how much fun I have doing this kind of random stuff. Those are negative. Oh, let's go to 0. I think that's why we're getting something ridiculous right here, is because the MAP is not liking that we have so close to 0. I think that's where MAP will have problems. Yeah, there's little tiny numbers in here. I think that's causing issues. Well, that's got it. I don't know. I like looking at data. I like running things. I love running code. And if you like running code, if you like looking at data, you're in the right spot. I think we got office hours coming up your way. Is it office hours now? Oh no. Why would I put office hours so soon after class? No, we got 13 minutes. Time to go grab some food. With that, we will be back. We'll be doing some activity this week. So stay tuned. Simple linear regression activity coming up. Big help for the assignments. I think that's what people are doing. News and those. I'll see everybody later. Bye for now. Great job, Max. Keep looking into statistics and keep asking those questions for what you're doing. Excellent work. 100 points, Max. Bye, everybody.